Hi there. I started to come out here and do Hamlet's soliloquy, to be or not to be, that is a question. But somebody told me it was the wrong stage for that. So anyway, I'm Dave McAllister. I work for a little company that you may have heard of called Nginx. We're one of the most widely used open source packages in the world. Something like 64% of all web traffic flow through Nginx on a daily basis. But this talk has almost nothing to do with Nginx. This talk came out of a series that I do on data science for observability. And the piece that becomes really important for that is that when we start looking at scale, rules may change. But in one of my talks, there's one section that I'll actually get to as part of this talk that people would scratch their head and say, so how does that work behind the scenes? And when we started looking at this, we found out really quickly that we do a lot of numbers, but very honestly, most of us have no clue as to what the manipulation is anymore. This group is probably a little different, but when I'm talking to basically the pure dyed-in-the-wool observability guys, they really don't understand that. But to start with, I'm going to start with a simple question. What's the difference between mean, median, and mode? And I'm watching around the room and seeing people go through this. And most of y'all probably got mean. Somewhere between 68% of you understand median. And somewhere around 35% of you probably can remember mode somewhere in the past. But if you got all three of those, by the way, let's add in the extra credit question. What's the 9th data kind number? It was just discovered, like end of last week. It was finally published for the first time. So if you actually know what the 9th data kind number is, great. Come up and do the talk for me instead. So monitoring is a numbers game, very honestly. Standard red dashboard, rate, error, duration. Inside of that dashboard, there's a lot of information that's happening behind the scenes. I have aggregation going on one part of this. That aggregation is over a 10-second period. I also have strip charts that are showing me this data in real time. And I have percentages that are going on. I can also have alerts set up around this. Those alerts can be lots of different things for here. You can be looking at an average. You can be looking at historical anomaly. You can be looking at all those different pieces. Generally, and it has to be, they're time-stamped. So we know what order they came in here, and they're usually key value pairs. Timestamp, metric name, metric number. Metrics, I'll do these things. Data, to be useful, has to be aggregated. We can't sit and watch our data on scale flow through like you're doing a tail minus f on a log file. The data is too much now, so we need to be able to aggregate it. We need to be able to analyze it. We need help to be able to look and find out what's going on. No one is going to be doing a running 10-second average going across these models here. And then finally, it has to be visualized. Honestly, visualization is less of a characteristic here, but as we all know, dashboards sell executives and executives pay the bills for the tools. So those are the pieces that are going on there. And it tends to answer some interesting questions. So we now understand what the alerting structure looks like, but how do you deal with outliers or spikes in your monitoring? Remember, spikes can go both ways, up and down here. How do you get a representative value between vastly different quantities? So when you're comparing things together, are you picking the right piece, the right statistics? How do you arrive at values that represent the rate of change? And then finally, the real question is, what's the alert really telling you? So keeping those things in mind, and we're going to go through some of those aspects. So my starting question, mean, median, and mode. Here's a data set. I think it's like 31 numbers put together here. The mean is a measure of central tendency that represents the average value on a set of data. And in this case, those numbers add up to 5.444. The median is the middle value of the ordered set. So put all the numbers in order, pick the one in the middle. If you got two in the middle, average them together. And the mode is the one that appears the most often. In this case, the mode is 1. So back to this mean thing. Our mean is 5.4 and change. Or is it? Is the mean 4.13 or is it 2.791? And the answer is yes. Because this was a trick question when I started off. The one you're all thinking of is something that's known as an arithmetic mean. And there can be lots of different means here. We can have arithmetic means, harmonic means, geometric means, trimmed means, weighted means, moving means, all given together. Each of these has a potential use as well as a potential drawback. And they give you different insights to your data as each piece goes forward. Almost all of these are implemented somewhere in your monitoring software, and the ones that I'm going to talk about that aren't, I'll give you the pointers to R, and most monitoring software just pulls in an R function without any words inside of here. But as you can see from that first number, they can give you really different results based on what you're looking at. It makes like and unlike comparisons a lot easier if you can understand which of these you use at which particular time. So the one everybody thought of, this is the most common, arithmetic. Add the things together, divide by the number. That's very central. It's the central point in a normal distribution. It is not the 50% mark unless your central point is 0 and your standard deviation is 1. So you can't say the mean is 50% up or 50% down. Interesting piece of information, but most of us automatically assume mean is 50%. Not there. It's very useful for comparing to previous conditions here, and it usually gets aggregated in monitoring into a little time series, either a moving time series, where I'm going to pull the last 10 seconds of data as it moves across, or in a batch process where I'm going to put 10 seconds in a batching process. In a time series, we usually need to constantly reevaluate, add the new data in, subtract the old data out as we're moving across. This gives us the best trend lines that we can look at. So here's a simple little load balancer example. I have a load balancer that's feeding into 3 systems, 33 requests per second, 5 requests per second, 1.6 requests per second. The arithmetic mean adds those together, divides by 3, and comes out with an arithmetic mean of 13.33 requests per second. Looks like a very solid, sound number. However, this has a tendency to weight the largest value heavier than any of the other values. So, when we look at this problem, we have geometrics, another central tendency inside of here. This one's a little more challenging. However, computers are now fast enough to deal with this. Back in the old days, you would have needed a Cray 2, 1991 Cray 2, or something to calculate the geometric mean of a 100-item object, because you multiply all the values together, and then you take the nth root. So the 100th root of 100 things multiplied together. Today, computers laugh at you when you do that. They give you the answers almost instantly. Even Microsoft Excel will do that, blink of an eye for this. In DevOps, we find this used in the number of deploys per unit of time, how often we're deploying. This becomes an indication of those things here. Or the lead time to changing. How often are we changing things for this? Mean time to response, mean time to recovery, all become part of this. But in this case, I'm going to use throughput, because throughput is something that's got a unique concept when it comes to a geometric mean. Same load balancer example, same numbers over this, but my geometric mean is 6.525 requests per second. This number is actually the number you would get if you took those 3 systems, crushed them into one system, and ran that without a load balancer. That's actually the balance number that's showing up in a load balancer model. The geometric mean gives you that number. So keep this in mind that when you're looking at different pieces here, arithmetic means are easy and commonplace, but it may give you a false indication of what's actually going on in the system. So the third of these, what are called the traditional historical whatever, is harmonic. And harmonic means are used where we have different systems that we're trying to compare things across those things. The harmonic mean weights the lowest number heaviest. The arithmetic mean weights the biggest number the heaviest. And so when you look at these two things, this will give you the balance across looking at the lowest possible value. So This one, you take the reciprocals, you add the reciprocals together, and then you divide that into the number of units. So in DevOps, we find this as a performance over range. You'll find this used in things like latency, throughput, where the numbers come into play, and the numbers have different values that are not necessarily equivalent. And so here I'm using a computing example, fairly straightforward. My CPUs are running at percentages rates. My first one, I've got 30, 40, 20, 10. You read the numbers here. My harmonic mean, it says that that system is roughly 20% utilized. An arithmetic number for that, if I remember what that number is, of course I didn't write it down here, is substantially higher because it is going to weight the 40 higher. And I think if I remember correctly, it comes out at about 22. So not too much of a variance. But when you suddenly spike something, and in this case, node 4 spiked to 80, node 3 dropped to 10%, my harmonic mean jumped, even though I lowered the lowest value. And this is a problem with this. An outlier spike for harmonic mean may give you a false indication, false positive indication. So 3 simple little mean structures, arithmetic, geometric, harmonic. Why don't we ever use those other 2? They're incredibly powerful. Well, there's a single reason that we tend not to use them, and that's that anything that has a 0 value in it destroys them. So harmonic mean, I'm dividing by the value. 1 divided by 0 is not defined. In the geometric, I'm multiplying by the value. Any number times 0 is 0. And so therefore, we have to make sure that if we're using one of these, we're providing them real values. The real values are important going across each of these pieces. So the second part of this median, where we have the central value. Now, the interesting thing is, I told you that mean is only 50% under certain particular rules. The median is always the 50% mark. 50% is higher, 50% is lower. So if you're looking to do a 50% comparison, P50, P50%, the median is your mark. It's higher than that, it's over P50. It's lower than that, it's less than P50. And so here's a simple case. This is actually a trace of request data coming in again. Request data coming through here. The median at the endpoint here is 26, and the mean is 25.25. The first few values, by the way, are meaningless in statistics. Statistics is an aggregation. We do not have statistical meaningful relationships with a single number. And so when we look at this, you're going, it's pretty close, pretty cool. But I mentioned, for instance, historical anomalies. Say, for instance, you are looking at your sales on every Friday, and you're running Fridays back for 3 months. And all of a sudden, something happens, and you get a spike. And all of a sudden, that data is no longer in that lower edge range, but I now have an outlier that's 250. My mean jumps like crazy. Alert time, boom, bing, bang, bing, bing. Alerts almost anything on this. However, that mean does not return to the standard value. So it will be a period of time before it calms back down to what you're looking at, which means that your alert, if you're set off that mean, that arithmetic mean, may not find things for several periods of time. The median, on the other hand, jumped from 26 to 26.5. And in these cases, what you'll find is that the median is a much more stable approach to looking at your baseline for an alerting structure, particularly in anything that's looking at historical anomalies or sudden change. The median will give you that data against the current data point more accurately over time once you've established what that is. Now, just to pull it back in to play a little bit here, harmonics can also be used. They are an indication of the median structure. And that median structure, again, if you can see what's going on, the harmonic is the bottom line, the median is the middle line, and the mean is that blue line at the top. Harmonic changed a little bit. Median changed a little bit for this data set. Mean jumped way up. And so you can, if possible, use that. It's a lot easier to calculate the median than it is to calculate a harmonic. So I strongly recommend that you take a look at what the median can do for you in your learning structures. So mode. Mode is most commonly recurring value in a set, usually as a histogram, and not very often used. Generally speaking, we find modes showing up when we do log analysis for this. You'll see it's showing up in security monitoring. Is somebody having a lot of failed attempts at login? Or you can look at user behavior. What is the normal pathway that a user is going through? And we can start looking at those as inferentials. That structure is really useful when we're doing the secondary deep dives. The metrics will usually tell us that we have a problem occurring on. The mode will help us understand why the problem is occurring, especially if it is a reoccurring problem. And so the mode is most useful in this inferential space. So distributions for this, I'm not going to cover too many of these, but again, probably most common with the normal or Gaussian distribution. That's our famous bell-shaped curve here, but there's lots of other things in here. You probably made some use of what's called a beta distribution. A/B testing is a beta distribution. Two binomial objects, which one wins? And each of these pieces, again, can have different structures and different pieces. A little deviation. To talk about distributions, we have to talk about standard deviation. And this measures the variability, how much your data varies across this, and can help you identify trends and outliers. It is not percentage-based, unless you're doing this thing called a coefficient of variability, in which you make it into a percentage. But it can give you a percentage indication. In a normal curve, one standard deviation is roughly 68% of all the data under that curve. And you can read it, 95% is 2 standard deviations, 99.7 is 3 standard deviations. Why? This gets used a lot when we start looking at things like lead time. How long did it take us to respond to something? What's our standard deviation across that model? Or what's the recovery time? Or how many anomalies are we seeing? Each of these pieces gives us a different set of information. The standard deviation is near and dear, and it's an underlying for almost every distribution of some sort. But I want to cover a couple that you probably have never had a lot of time looking at. This one's called Weibull. And Weibull is time to failure analysis. So this is how you can figure out what the odds are that you're going to lose something over a period of time. Here I took a simple little hardware system. My old spinning Rust disk has a 500-hour time to failure model for this, memory, so forth, down to the solid-state disk, which is actually the most stable piece here. Don't ask the math. I don't have enough time or slides to put it up. But R does it all for you. And so when you're dealing with this, you simply find 2 pieces. You find basically the shape and the scale parameter by handing it this data. And then from there, you can do the next call, which says, what is the probability of failure of given this shape and scale of data for a period of time? In this case, my things all go up to 2,500 hours. So I said, what's the probability of the system failing at 3,000 hours? And it turns out it's roughly a 30% chance that something in the system will fail inside of 3,000 hours. This gives you an indication of where you may be approaching end of life in a distribution curve based on what your risk factors look like. Weibull is kind of fun to deal with. It gets used in certain cases, but Weibull is also a case where we look at different data, different ways to make sure that we're making sense. An exponential is how we measure those things that are occurring at random intervals that we don't have any foresight on. User requests coming in, messaging services, RabbitMQ, those things. We don't know when they're going to arrive, but we can measure when they have arrived. Similar thing, complex math, but again, on our library, the math library does this for you. And we're going to grab these pieces. And so, yeah, using the same example, Within 5 seconds, I've had 120 user requests come in, down to 10 at 20 seconds. I build that structure, that rate estimate, by simply making the call to give it that data. And then I get a rate number. And then I can say, what is the probability, what's the percentage that within a certain amount of time, I am going to see a call come in, a user request come in. In this case, I said, what is the probability that within 10 seconds a request is going to come in? And it turns out it's about 40%. And so this can give you the ability to look at things that are not directly related, but inferential to the overall environment. Which does give us this next thing, descriptive versus inferential. I've mentioned inferential twice. Inferential is when you don't have every single piece of data in place and you're putting the data together and you're making judgments based on the data that you actually have. Descriptive is when you have every piece of data and you can simply calculate the final result. So when you're drawing the statistical conclusion, having all of the data is really, really useful, but we have a heck of a lot of data coming in. Had a customer at a previous company, when it was in this space, they did 48 terabytes of log files per hour. They can't actually analyze all the data that's coming in. And so they have to make choices about what their data looks like. Inferential uses that sample set, and they can use that sample set to figure out their conclusion. They can test against hypothesis, they can use it for visualization. The problem is that the minute we start touching inferential data, we're starting into sampling. And sampling has its own headaches. Monitoring is a data problem. We have more data coming in. The observability signals, which have shown up on the screen multiple times, metrics, traces, logs. Analysis is usually aggregated. It's analyzed in segments. What do we do? What data do we pick? And generally speaking, there are these methods of dealing with sampled data. And they can be purely random down to what's called purpose-led, purpose. I used to be able to pronounce that word, sampling. The samples that are coming in color your statistical conclusions. So, head-based sampling in the tracing world versus tail-based sampling in the tracing world. Head-based sampling, purely random. When a trace starts, I've decided I'm going to keep that trace. I have no idea what its conclusion is going to be. Tail-based sampling, when the trace ends, I'm going to look and see what the result of the trace was and make a purpose-led decision on whether I'm keeping it or not. Was there an error? Did it cross some boundary of time? The problem is that when you're looking at sampling, in either case, head-based sampling will miss whatever your percentage things are. You're sampling 10 out of 100, and that means 90 of them, you have no idea what happened. Tail-based sampling, you've got this wonderful thing, you know everything that went, quote, wrong, but in observability, part of the message is the unknown unknowns. When something happens that we don't know could happen, how do you find it on a tail-based model? And so we have these purely random to not purely random, where we go from retention rate as coverage to fault rate as coverage. And so sampling leads you to different conclusions. If you just grabbed numbers from a tail-based sample, you may find that things look really bleak. If you look at head-based sampling, you may find things look really good. Similarly, in this case, I'm looking at a head-based sampling based on the data, and it came down and said my latent distribution is 1 to 2 seconds. All gloriously good. 3.7 seconds or less, I'm happy with. When I look at all the actual data, I have at least one that's 29 to 40 seconds. I have an unhappy customer. Hopefully he regenerated his request. 3.7 seconds is likely to cause somebody to leave your site. So that data structure becomes a really unique case. Now the good news is metrics are not usually sampled. That's not always true when you're looking at metrics generated from tracing. And so red metrics usually and should never be sampled. but quite commonly are. And it doesn't give you the ability to do that forensic link back because the data that you derived from may no longer be there. It is a necessary evil, but understand what you're getting into when you look at statistics generated from sampled data. So, quick summary for this. Statistics are how we measure or analyze our metrics. And there's a statement, incorrect, that I always like to point out. It says, on scale, probability is not your friend. Wrong. Statistics is not your friend. Probability is one event at that moment. It has nothing to do with scale. Statistics is all about scale for that. And the statistics tend to be aggregation and reduction to show those central tendencies. That's where we do. That's why they don't show individual behavior for this. Most of us make choices of very few basics. And by the way, that's a great approach to doing this, as long as you understand why you're choosing to use those specific basics. And finally, my favorite line, my favorite quote of all time. Brian Kernighan, 1979, Unix for Beginners. The most effective debugging tool is still careful thought, coupled with judiciously placed print statements. Statistics allows us to make those print statements meaningful. And with that, I'll turn this back over. My slides are on GitHub. I'm sure they'll be distributed. You can find me on LinkedIn. You can find me on the Nginx community site. And with that, I'll turn it back over. And thanks.
Awesome, thank you.
By the way, one last thing. That's the Dedekind 9th number.
Awesome. Any questions for Dave from the audience? Do a quick scan here. Make sure.
Silence is the usual response to this talk.
Exactly. Well, what's funny is, as I mentioned before, I've been doing this series of like people pronouncing words, and I actually tossed in Nginx, which is how I pronounce it, and I was actually curious if anyone would pronounce it differently, and surprisingly, it was like out of 31, there was like one person who pronounced it differently. But
you do know that the first N is silent.
The which one?
The first one.
The first N?
Yes, and that's name is Jinx. You probably can't see it, but this is Jinx.
So wait, how do you pronounce Nginx?
Nginx.
Oh, God. Bam. Got me. All right, let's do a big round of applause for Dave. Thank you so much.